Today, we are undertaking a fascinating mission on how to detect meaningful trends in environmental data. Think climate change, long-term pollution levels, or, anything measured over years. How can you reliably spot the actual trend when the data is just screaming noise at you?
Yeah, it's one of the biggest statistical challenges facing environmental science right now. And the difficulty, it really comes down to the nature of the data itself.
How so?
Well, when you measure temperature or pollution over consecutive time points, those measurements just aren't independent. If it was cold yesterday, it definitely influences today.
Right.
This high degree of temporal dependence makes classical trend analysis almost useless sometimes.
And that dependence, it basically throws the entire reliability of older methods out the window, doesn't it?
That really does.
The sources we explore today highlight two critical flaws in those traditional approaches, like the old workhorse, the Mann-Kendall test. First, they fail because of what we call the dependence effect. And second, they simply can't capture complex trend shapes. They're looking for a straight line when the environment is building a roller coaster.
That's exactly the insight.
Yeah.
We needed a tool that wasn't just looking for that straight line, but for a complex curve. A tool that could actually see the bends and turns.
Okay.
The core solution proposed here is a powerful new testing procedure. It's a kind of fusion of localized statistical smoothing and a highly efficient simulation technique, specifically designed to detect smooth, non-monotonic trends, even in data that is massively autocorrelated.
All right, let's dig into that.
Okay.
Let's unpack that dependence effect first. Autocorrelation, you said. It means your current reading is correlated with past readings. We see this everywhere in environmental data.
Right, everywhere. And because classical tests were developed, decades ago, assuming perfect independence between data points.
Right, like in a lab setting, maybe.
Exactly. So when applied to environmental time series, they are, as the researchers put it quite bluntly, inapplicable.
Inapplicable. Wow. And the consequence of ignoring that dependency is huge for you, the informed observer listening right now. It means even minor temporal dependence can wildly skew your results.
Absolutely.
You might end up inflating your significance levels, thinking a trend is real when it's just noise. Or conversely, you might fail to find a real underlying trend because the noise is just, hiding it. This leads to unreliable or even false conclusions.
Yeah, and we have a perfect illustration of this consequence involving the ice break updates on Lake Baikal.
Oh, interesting. What happened there?
Well, earlier studies, which assumed independence, they confidently declared a statistically significant linear warming trend. Clear as day, they thought.
Okay.
But when later researchers reran the numbers, incorporating the actual dependence structure present in the data, using a sophisticated sieve bootstrap method,
They got a different result.
they reached the opposite conclusion. The clear monotonic trend everyone thought they saw after the 1920s. It simply vanished. Gone.
Wow. So the structure of the dependence was basically creating a phantom trend.
Exactly. It was telling a false story.
That Lake Baikal story is a perfect illustration of how dependency tricks us. But okay, even if we manage to fix that dependency problem, we still face a second massive challenge, right? We're still kind of forcing the environment to follow our simple statistical rules.
Precisely. Traditional methods, they pretty much assume the trend is a simple straight line increase or decrease, what we call monotonic.
Just up or just down.
Right. But real-world systems, especially climate dynamics, they're full of sudden shifts and change points. These aren't smooth ramps.
Like the famous Pacific climate shift of 1977. That was a huge jump, wasn't it?
A huge one. A game changer for oceanography and global weather patterns. And that's the kind of systemic change that simple linear models just completely miss.
Right.
One analysis cited in the paper showed that when you actually included the information about that 1977 regime shift into global temperature models, the conclusions changed substantially.
How substantially?
Trends previously declared significant were suddenly found to be insignificant.
So if you miss a major regime shift like that, you're not just missing a date on a calendar.
No, you're potentially basing billions of dollars of policy decisions on a false premise of constant, smooth change. It's a big deal.
So if the trend isn't just going up or just going down forever, if it's like that roller coaster you mentioned with curves and bends, what do you call that? What's the term?
That's non-monotonicity. And the authors are really clear on this. We need to drop the assumption of linearity altogether. Instead, we need to test whether the trend is of a smooth, non-monotonic form. We need a tool that can actually detect that roller coaster shape.
Okay, so that brings us to the core of the breakthrough here. This new non-parametric trend test, the WAVK procedure. What makes this WAVK method uniquely suited to this messy environmental data?
Its power really lies in its flexibility. First off, it is non-parametric, meaning it doesn't assume the data follows a specific shape, like a bell curve. And it's fully data-driven. It learns from the data itself.
Okay.
This robustness is just essential for environmental measurements, which are notoriously messy and often lack a perfect, known noise structure.
And it handles two really tricky types of noise that you often see in these long-running environmental series, right?
Yes, exactly. First, it deals with processes that have very long-lasting autocorrelations.
Yeah.
So noise that doesn't easily fit into simple, short-term models. And second, it handles data where the noise itself is volatile. Think of it like this. In a stock market, the variance changes all the time. That's volatility.
Right, big swings, small swings.
Exactly. In environmental data, the volatility of pollution or temperature readings can also change over time, sometimes quite drastically. These are complex statistical models. But WAVK is specifically designed to sort of ignore that changing noise structure and still find the underlying trend signal.
So, okay, before we get to the final test result, you have to clean the data up first, right? I saw the paper mentions pre-filtering using something called an AR process. What's that step trying to achieve?
Yeah, that pre-filtering is crucial. Since we know the data is autocorrelated, yesterday influences today, right?
Right.
We have to filter out that temporal dependency first. We use an AR filter, an autoregressive filter. And the key is the order or complexity of that filter is estimated by the data itself using criteria like BIC.
So it adapts to the specific data.
Precisely. The goal is to essentially remove those yesterday influences.
So you're trying to turn the correlated data into something that looks more like random white noise, like static on a radio?
That's a great analogy, exactly.
Right.
Once we've pre-filtered, then the method applies this local regression technique.
Local regression, so not one line for the whole data set.
No, exactly. Instead of fitting one single straight line to the whole data set, it looks at tiny distinct time points and constructs a sort of local window around each one.
Ah, okay.
This lets the statistic capture the exact localized shape of the trend, point by point, rather than just averaging everything out across the entire series. It sees the bumps and wiggles.
Okay, let's talk computation, because these environmental data sets are often massive, hundreds of years of readings sometimes. Running repeated simulations, this Bootstrap thing, it must be incredibly slow, right?
It usually is, yeah.
What magic did the researchers use to make this whole process fast enough to be practical?
That's really where the innovation lies. The flexible and computationally efficient hybrid Bootstrap procedure. Traditional Bootstrap methods for correlated data are notoriously slow because you have to simulate the entire complex history again and again and again.
Thousands of times, maybe.
Easily. And the goal of all that simulation is just to reliably figure out the true distribution of your test results, because the data is correlated, correct? You can't use standard tables. But the key statistical insight here is actually quite clever. It turns out that the distribution of this WAVK statistic only depends on the second-order moment structure of the time series.
Second-order moment structure, meaning?
Right. So covariance structure, how strongly related points are at different time lags. And this structure, crucially, can be approximated quite well by a simpler AR process.
The same kind used for filtering.
Exactly. Even if the original data had complex nonlinear dynamics, the volatility changes we talked about.
Okay, so that's why it's a hybrid approach. It mixes things up.
Precisely. It means they can use a much faster parametric Bootstrap. This relies on simulating normally distributed random variables based on that estimated AR structure, instead of relying on the much more computationally intensive non-parametric resampling methods, which involve shuffling the actual data.
Got it. So simulating simple numbers is way faster than simulating the complex original data over and over.
Way faster. It saves a significant amount of time. And we should probably mention that sidebar finding about model selection too, when choosing how much filtering to apply with that AR model.
Yeah.
They found they generally preferred using the Bayesian Information Criterion, or BIC, over the Kaike Information Criterion, AIC, especially for smaller samples.
Why does that distinction matter to us or to someone using this?
Well, essentially, BIC is stricter. It penalizes adding complexity to the model more heavily than AIC does.
So it prefers simpler explanations.
Right, which is usually better when your main goal is hypothesis testing. You want to find the clearest possible trend signal and avoid accidentally fitting the noise, especially with samples that aren't absolutely huge. AIC can sometimes pick overly complex models.
Okay, that makes sense. Stricter is better for testing. So for you, the listener, the major opportunity opened up by this new WaveEK method is the ability to assess the shape of the trend, not just asking, is there a trend? Yes or no.
Exactly.
The WaveEK test allows researchers to test if the null hypothesis of a specific trend shape, say a linear trend, is actually true, versus the alternative that the trend is something else, something more complex.
And that ability has direct implications for identifying those critical regime shifts we discussed.
How so?
Well, if the test rejects the simple linear assumption and accepts a non-monotonic form, like, say, a quadratic or a cubic trend.
A curve.
Yeah, a curve. That provides immediate insight into the existence and maybe even the number of potential change points. The peak or the valley of that curve corresponds pretty directly to a regime shift.
I see. The turning point is the shift.
Exactly. And the simulation results in the paper really prove just how necessary this capability is.
Yeah.
WaveEK was competitive in finding those typical expected linear trends, the easy ones. But when they tested against detecting complex non-monotonic alternatives, like polynomial curves or even sinusoidal wave-like patterns.
Which happen in nature.
Absolutely.
Yeah.
The conventional tests, like Mann-Kendall, showed very low power. They were basically blind to those shapes.
They just couldn't see them.
Couldn't see them at all. Whereas the WaveEK procedure maintained a highly competitive performance in those challenging non-monotonic cases. It's truly an essential diagnostic tool for seeing beyond just the straight line.
Okay, let's see this method in action then. You mentioned two real-world case studies that really demonstrate that contrast. First up was Turkey Lake water pollution data, right, from 93 to 2002, weekly sulfate pollution.
That's right. And the data was messy, strong seasonality, definitely not normally distributed, typical environmental data.
And what did the traditional methods say?
Well, in this case, the classical results were completely inconclusive. The standard t-test and the Mann-Kendall test, even when they tried modifying Mann-Kendall to account for the dependence, they did not reject the null hypothesis of no trend. The p-values were really high, 0.635 and 0.552. Basically, they saw absolutely nothing happen. No trend.
Wait, let me make sure I heard that right. The standard traditional analysis said there's absolutely no trend here. Move along.
Pretty much nothing to see.
But what did WaveEK find?
WaveEK detected a change so significant it rejected the null of no trend, with a p-value of less than 0.001, highly significant.
Wow.
And furthermore, when the researchers then tested against the possibility of it being just a simple linear trend, WaveEK also rejected the linear trend, with a highly significant p-value of 0.004.
So that's not just finding something new, that's completely overturning the existing conclusion.
Precisely. The final conclusion was that the sulfate data exhibits a clear nonlinear deterministic trend, which is actually supported by just looking at the plot. You could see apparent change points around 1997 and 1998.
Oh.
The WaveEK test successfully uncovered a complex trend that the traditional, simpler methods missed entirely.
That's a striking difference. Okay, what about the second case? A much longer data set, right? Toronto air surface temperature from 1841 to 2011.
Yes, a really long one. Monthly mean temperatures. And again, it showed seasonality and also evidence of that changing variance over time, those volatile air SEH effects, even after they filtered it.
So what did WaveEK find in over 170 years of temperature data?
Well, in this long-term temperature data, the WaveEK test again showed its sensitivity. It rejected the null hypothesis of a simple linear trend with a highly significant p-value, again less than 0.001.
Rejecting a linear trend in long-term temperature data, that is a very strong finding. If it's not just a straight line upwards, what does it suggest we should be looking at instead?
Well, it strongly suggests non-monotonicity in the long-term trend. When they visualized the smoothing curve from the WaveEK analysis, it revealed some interesting complexities. Slight convexity, like a gentle upward curve in the 19th century, and then slight concavity, a gentle downward curve relative to the overall trend in the 20th century.
So not just steadily increasing at the same rate?
Exactly. It clearly challenges the overly simple assumption that global temperature, or at least Toronto's temperature, is just increasing in a perfect straight line. It offers a much more nuanced view of the climate dynamics over that long period, suggesting perhaps a shifting pattern of warming over the last 170 years.
Fascinating. Okay, let's try and wrap this up.
Sure. To synthesize all this, the WaveEK test really emerges as a critical new diagnostic tool. It's incredibly valuable for environmental research because it gives us a reliable method for identifying these complex, possibly non-monotonic trends.
The roller coasters.
The roller coasters, exactly. While simultaneously handling the high degree of temporal dependence and the noisy characteristics that are just inherent in this kind of data, it fundamentally shifts the analysis from simply asking, did change happen, to, okay, what is the exact shape of that change?
So what does this all mean for you listening in? This methodology gives researchers a genuinely powerful way to distinguish between different trend forms, say linear versus a much more complex cubic shape, and to assess potential regime shifts without having to guess or assume prior knowledge of the underlying noise or the dependence structure. That's a massive leap in reliability, isn't it? It means we can trust the conclusions drawn from environmental data far more than perhaps we could before.
Absolutely. And the research even points toward future possibilities, including extending this method to analyze what are called long memory time series.
Long memory.
Yeah, where the dependence lasts for a very, very long time. This is highly important for hydrological applications like analyzing river flow or long drought cycles.
Which raises kind of an interesting final question then. What other complex, long-running environmental data sets, maybe things like deep-sea core samples, ancient tree rings, or Greenland ice records, could be holding surprising non-monotonic truths, these hidden curves, just waiting to be revealed by these powerful new curve detection tools?
That's a great question to ponder.